Here we have a data set from the StatCrunch collection of data sets that has the variable make and model of a vehicle. And the variables that we're going to look at are the horsepower rating then for this vehicle, so we can see that in this column, and the fuel efficiency rating for this vehicle in miles per gallon. Now, something that we expect is that as the horsepower generated by the power plant for this vehicle increases, we would expect that the fuel efficiency would decrease. Requires more gas to produce more power. So let's look at the graph. We'll click Graph, Scatter Plot. We're thinking that horsepower will have an effect on the fuel efficiency in miles per gallon. Let's click Compute. And we're not seeing a line here this time. This appears to have a very pronounced curve. So let's go look at the regression. So we'll click X variable horsepower, Y variable miles per gallon, and let's look at the fitted line and the residuals versus the X values. We might note that assuming this to be a linearly related data set, the correlation coefficient is minus 0.790 if we round to 3 decimal places. We look at this line and it is very clear that this data set does not have a linear trend. It appears to have a very strong curving trend. And if we look at the residuals versus the X values and look at the line Y equals 0, we see that this is definitely not a random looking pattern above and below the line Y equals 0. So the first thing we think about doing then is logging the Y values, and we're choosing the miles per gallon to be the Y values. So we'll click Data, Compute, Expression, Build. Now I am going to click Log 10, Add Function, and then I want miles per gallon is what I want to get a log value for. We're first going to log the Y values. And this puts a new column in our sheet here. So now we can do a regression where we have horsepower versus the log of the fuel efficiency. So let's click Stat, Regression, Simple Linear, Horsepower, Log of the fuel efficiency, plot the fitted line and the residuals. Click Compute. And what happened to our R correlation coefficient here? It got a little better, actually. It went from minus 0.790 to minus 0.857. Let's look at this graph. Wow, even when we have the log values, we still have something that looks like a curve. And this residual plot still did not result in a random distribution above and below that line. It still looks like a curve. So when that's the case, the thing we'll do then is go ahead and log the X values. So we'll click Data, Compute, Expression, Build, and we're going to log base 10, add function, horsepower, add column. Click OK and compute, and now we have a new column here. So the log of the horsepower will become the X coordinate, and the log of the miles per gallon will become the Y. So we'll click Stat, Regression, Simple Linear, log of horsepower for X, log of miles per gallon for Y, plot the fitted line and the residuals, click Compute. This R correlation coefficient got even better. Now it's minus 0.915. Now we have something that looks quite a bit more linear. And this scatter plot of the residuals versus the X values does have more of a random looking distribution to it. It's definitely not perfect, but out in the real world, you're very rarely going to find perfect fits. So assuming then that this is a sufficient model, let's get a look at what we need to do with it. This time the relationship is the predicted value for the log of the miles per gallon or fuel efficiency can be found by 2.866, let's go to 3 decimal places, minus 0.669 times the log of the horsepower. Now, the problem here is that when we go to trying to make predictions using this model, we'll plug something in for horsepower, we'll log that, we'll multiply it by a value, subtract that from another value, and what'll come back will be the log of the fuel efficiency. Well, it would be really nice if we could plug in a horsepower value and get back a miles per gallon value rather than the log of a miles per gallon value. So what we need to do is manipulate this expression or this equation using the rules of logs and exponents that we know about so that we can plug in values for horsepower and just get back values for the miles per gallon. So we'll do a little bit of remembering about how this works. We could convert this to its corresponding exponential equation by saying miles per gallon predicted is equal to 10 raised to the 2.866 minus 0.669 log horsepower. And then we start thinking about, okay, well, how does this thing work? Well, we subtract exponents when we're dividing with like bases. But something that we might want to do here is rather than subtract, we might want to add so that we use the rule when we add exponents, we multiply with like bases. So I think I'm going to do a little bit of manipulating here. And remember that subtracting is the same as adding the opposite. So I could call this plus minus 0.669 log horsepower. But then I also remember that when I multiply a value out in front of a log, it's the same as having it up in the exponent. So this then would result in the predicted value for miles per gallon would be equal to 10 raised to the 2.866 plus the log of the horsepower raised to the minus 0.669 exponent. So now we'll use that rule that says that when we add exponents, we do that when we're multiplying with like bases. So we'll have 10 raised to the 2.866 times 10 raised to the log, and remember this is base 10 if we don't write anything here, of horsepower raised to the minus 0.669. Now we can go ahead and get ourselves an estimate of what this value is, 10 raised to the 2.866. So we'll have the predicted miles per gallon will be equal to, and if we round this to 3 decimal places, we'll have 734.514. And then we think about, well, 10 raised to the log base 10 of this quantity is really just this quantity. So then we'll just multiply this by the horsepower rating raised to the minus 0.669. So here's our relationship then. I can plug in a value for horsepower and get back a value for miles per gallon.